So quantum numbers are essentially the address okay, come on, be nice. Where the electron is most likely to reside. You notice the word most likely. That most likely is there because of the Heisenberg uncertainty principle. So it is most likely to reside. Now, you will notice when I described where you were located, I started out big, and then I slowly narrowed it down further and further. The quantum numbers do the same thing. And folks, at this point in time, I just need you to get the quantum numbers and their rules down. We are going to then, on Thursday, start getting into electron configurations, which is the electron's address. And as we do get into those electron configurations, then we'll apply these quantum numbers to a greater extent. But today it's about getting an understanding of the quantum numbers and how these quantum numbers are derived. So the very first one that we're going to talk about is the principal quantum number, which is represented with a lowercase n. This describes the shell or energy level where the electron resides. Compared to the nucleus. It is any whole number, 1 or greater. When we think of it, this is one area where the thinking about the Bohr model helps. You have your nucleus. Surrounding the nucleus, in that first orbital or first shell, would be the first electron we would add. The shell increases as you move away from the nucleus. So what we can say is that where the electron resides or let's say primarily resides, leads to understanding the size of the atom. This is also going to lead to our understanding when I get to it, what is known as Z effective, which is the effective nuclear charge. So that's our first quantum number. It's just a whole number. It describes how far from the nucleus the electron resides. And it's going to be related, as I said, to our Z effective later on. It's also going to be related to ionization energy. Which will be the energy required to create a cation. It's related to the reactivity of an element. So that first quantum number is quite important. The next quantum number is known as the angular momentum quantum number. And it is represented with a lowercase l, which I always use a cursive L to distinguish it between one and an L. This is going to be any value from 0 to n-1, where again, that n is that principal quantum number. Now, when we do this calculation, if L equals 0, It means that we have an S subshell. What that means is that the electron resides in a spherical shell around the nucleus. L can also equal 1. When L is equal to 1, then you have a P subshell. It means that the electron resides in a dumbbell shape subshell. Basically, if this were the nucleus, then the electron is in these lobes around the nucleus. L can equal 2. In which case we're talking a D subshell. In 4 out of 5 D subshells, or D orbitals, I should say, the electron resides in a clover leaf, or in the lobe of a clover leaf. So again, if this is our nucleus, and I'm talking about a D, then we're going to have a 4-leaf clover. L can also equal 3. And that is an F subshell, and I can't draw an F subshell. As of right now, though things may change soon, we don't have any electrons in subshells greater than 3. Though technically you can have an L of 4, an L of 5, an L of 6, and so on. Now, the next one is the magnetic quantum number. The magnetic quantum number is represented as an M sub L. And that is a lowercase m, not an uppercase M. This can be, basically this describes the number of orbitals in a subshell. If we're going to get specific, it basically describes where in an XYZ coordinate the electron is. This can be any value between a negative L to a plus L on a number line. The last one is the spin quantum number. And this one becomes important when we start dealing with multi-electron systems. It's represented as an M sub s. It can be a +1/2 or a -1/2. This one is necessary in order to follow the rule that no two electrons can have the same 4 quantum numbers. Basically, this boils down to a maximum of 2 electrons can reside in each orbital. Of a subshell. Okay, basically, folks, I've given you the rules and a lot of information about the rules. But what it's doing is it's narrowing it down. It's going, okay, so I said Arkansas. That's the principal quantum number. It tells you how far away from the nucleus the electron is. Then I'm going to narrow it down further. Conway. Well, that is the orbital shape. That is the angular momentum, the L, the angular momentum quantum number. What's its subshell, in other words? Then I'm going to go further, and I'm going to say Manion 102. That's narrowing it down to the specific XYZ coordinate of that orbital. And then I'm going to narrow it down further and say what C? That is it a plus 1/2 or a minus 1/2 spin? I'm narrowing it down to describe each and every electron. So for it to be a valid set of quantum numbers, they must follow the rules. N is equal to 1, 2, 3, and so forth. L is equal to 0, 2, n minus 1. M sub L is equal to a negative L to a plus L on a number line. And M sub S is equal to a plus 1/2 or a minus 1/2. All the 4 rules have to be followed simultaneously for it to be a valid set of quantum numbers. So let's look at this in action. So if n is 1, L can be anything from 0 to n minus 1. So in this case, it is valid for 0 to 1 minus 1, which is equal to 0. Therefore, the only option for L, if it is 1, is for it to be a 0. Now, folks, if you go back to what I said about L, that means that this is the first shell. Ugh. S subshell. Then we get to M sub L. M sub L is anything from a negative L to a plus L. So it can be a negative 0 to a plus 0, or in other words, it's equal to 0. So this says that there is only one orbital. And M sub S can be a plus 1/2 or a negative 1/2. And we do put them in that order. So in other words, we can have a plus 1/2 or a negative 1/2. And this is the actual electron, the orbital. So in the first shell away from the nucleus, the maximum number of electrons is 2. Questions? So so as far as valid, 1, 0, 0 plus 1/2, and 1, 0, 0 minus 1/2 would be valid sets of quantum numbers. Those are the only valid set of quantum numbers for shell 1. Let's do n is equal to 2. L is going to be 0 to n minus 1. So in other words, it can be 0 to 2 minus 1. Well, that means it's 0 to 1. So we have two options here. It can be a 0 or it can be a 1 for our L. Now, M sub L is a negative L to a plus L. Well, if L is equal to 0, then it's a negative 0 to a plus 0, or in other words, it's simply 0. But if L is equal to 1, then it is negative 1 to a plus 1. So if we think about it on a number line, that means that it can be a negative 1, a 0, or a 1. M sub S, excuse me, is either a plus 1/2 or a minus 1/2 in each orbital. So for 2, 0, 0, then our choices are a plus 1/2 or a minus 1/2. For a 2, 1, negative 1, our choices are a plus 1/2 or a negative 1/2. For a 2, 1, 0, our choices are a plus 1/2, a negative 1/2. And for a 2, 1, 1, our choices are a plus 1/2 and a negative 1/2. Now, let me explain what all that means. What it means is in the second shell, away from the nucleus, there are 2 subshells. An S subshell and a P subshell. That, folks, comes down to L of 0 is an S, L of 1 is a P. In the S subshell, there is 1 orbital containing a maximum of 2 electrons. In the P subshell, there are 3 orbitals each with 2 electrons. For a total of 6 electrons. In the P subshell. Take a minute. I want you to look at the quantum numbers and compare it to what I just wrote. And then I'm going to illustrate the first 2 on the periodic table, because it's related to what's up there. Okay. Questions before I get to periodic table? For principal quantum number 1, N equals 1. The only subshell that is valid is the S subshell. And it can house 2 electrons, a +1 half and a -1 half. That is why there are only 2 elements in period 1. It's because that period is representing the principal quantum number n. The fact that there's only 2 elements comes down to the fact that in the first shell, if you follow the quantum numbers, the maximum number of electrons we were allowed was 2. Now, other than the first period, which is a little bit different, starting at the second period, this group 1 and group 2 will represent your S subshell. In principal quantum number 2, the first subshell was an S. And in that S, there were 2 electrons. Hence the reason there are 2 elements across this portion of the main group elements. In principal quantum number 2, there was the P subshell. And the maximum number of electrons allowed in the P subshell were 6. 1, 2, 3, 4, 5, 6. This is the P group of the periodic table. This represents these. What I mean by that is the last electron for any one of these elements over here. The last electron is going to reside in a P subshell. Whereas over here, the last electron is going to reside in an S subshell. The quantum numbers play out on the periodic table. Now, once you get to the transition metals, they're a little bit different. And I'll be going into more detail on Thursday as to why. But this represents an L of 2. If you go back to when I was talking about the angular momentum quantum number, what did I say an L of 2 was? A D subshell. Without doing what I've been doing with the quantum numbers and listing them out, how many electrons do you think a D subshell can hold? I think I heard it. 10. That's because there's exactly 10 elements across the transition metals. This is your D block, meaning the last electron is going to reside in a D subshell. The lanthanides and actinides are known as the intertransition metals. They represent an L of 3. What is an L of 3? It's the F subshell. Guess how many electrons? Hold on, let me make sure that this didn't screw it up. Okay, they did screw it up. Minus the lanthanide and actinide, which some periodic tables will show it here, some periodic tables will show it here. Minus the lanthanide and actinide. How many electrons do you think a F subshell can hold? 14. Because there's 14 elements across minus the length of item X. So there's a direct correlation between this periodic table and all this quantum numbers. They may seem like just numbers, and they are, in fact, just numbers. But those numbers are like an address. And you can use those numbers to describe the address of every single electron in an atom of an element, which we will be doing some of. Folks, so let me just, with quantum numbers, let me ask you a couple of questions. Valid or invalid set of quantum numbers, and if it's invalid, tell me why. We'll go with that. Basically, for it to be valid, it has to follow those rules. So I always start out with rule number 1. Is the principal quantum number some whole number? Okay. Rule number 2. Says L is going to be 0 to n minus 1. Well, if it's 2, that means it can be 0 to 2 minus 1, which is 1. So it can be a 0 or a 1. Is it a 0 or a 1? Yes. M sub L has to be a negative L to a plus L, meaning it has to be a negative 1 to a plus 1. Is it a negative 1 to a plus 1? M sub S has to be either plus 1/2 or minus 1/2. So is this valid? This set's valid. Is the next one valid? No. Why is it invalid? Okay, that's one thing. That the M sub S can only be a plus 1/2 or minus 1/2. So it's invalid there. Is it invalid in any other way?
It's in the first shell. There's only one. Well, I guess two valid. It had 1, 0, 0.
Okay, you're on the right track. Yes. Okay, this second number, the greatest it can be is n minus 1. So the greatest it can be is 1 minus 1, which is equal to 0. So this one's invalid for 2 reasons. The angular momentum quantum number L is invalid, as is the M sub S. What about the next number? Is it a valid one? Doesn't follow the rules. That's all that matters, is it follows the rules. Yes, I have an N of 256, which probably will never exist. But all this has to be is, it can be anything up to 256 minus 1. So it can be any number between 0 and 255. It's valid. This one has to be a negative. So it can only be between negative of this number and a positive of this number. Since it is the negative of that number, it is valid. And a plus 1/2 minus 1/2 is always valid. So of these, the first and the third were valid numbers. Even though this one seems outlandish, technically it is a valid set of quantum numbers. We just don't have it on the periodic table. But technically it's valid. Questions? Making sure the clock is right today. Okay. So, because I introduced it, I'm going to finish with this piece today. And that is, there's a relationship between the periodic table and quantum numbers. Okay, this is my attempt at drawing. I do better at the periodic table than most things. I've drawn it so much over the years. Okay. So, subshells. Here, L equals 0, and it is the S subshell. Now, helium is an S, but the rest of it is a P. So over here, L equals to 1, and it is a p subshell. Here, L equals 2, and this is the D subshell. Here, the L is equal to 3, and this is the F subshell. Now, I'm going to call this from now on X. For the S subshell, X equals N. So in other words, for the S subshell, the principal quantum number is represented by the period number. For the P subshell, X also equals N, meaning for the P subshell, the principal quantum number is equal to the period number. Now for the D subshell though, N is going to equal X minus 1, meaning that the principal quantum number is going to be 1 less than the period number. And for the F subshell, N is going to equal X minus 2. So this is the 1S. This is the 2S and the 2P. Again, basically, I'm following the rules. This is the 3S and this is the 3P. The next one is the 4S, but when we get to the transition metals, N equals X minus 1. So this would be 4 minus 1, or in other words, these are the 3 Ds. 4P, then we go to 5S, 4D, 5P, then we go to the 6S, and this is where the N sub F, the F subshell comes in. It's X minus 2. If you'll notice, this first line should be in period 6 if I were to expand the periodic table. So 6 minus 2 is 4. So these are called the 4Fs. Then we come back to the 5D, 6P, 7S. Then we get to the 5F, 6D, and 7P. The quantum numbers all predicted where everything is. It's just the period number. And I'll show you more on Thursday why is 4S before 3D. I'll show you that on Thursday. You came in late. Here's the sign-in sheet.
So my partner, and she has
Her name on that, so I said, that's in the.
That's fine. I usually can find it.